They should fucking pregnancy test that bitch.
That's Hey guys, how are you guys doing?
Good. How you doing, Mr. K?
I'm doing good. So let's hold on for a second, let a few more people come in. Let's see. So we can go ahead and start. Any questions about some of the homework you're currently doing or the posted solutions I made for last week's homework? We can still talk about that, and then mainly with today we'll talk some about differential equations. That's our kind of topic for today. Maybe a little bit about statistics if you want to. I see one hand up, maybe. Go ahead, Caitlin.
I had a question about this week's homework.
Mm-hmm.
When I first looked at the homework, there were 6 problems, but now when I look at it, there's only 5. Was that 6th problem taken off?
So you must have looked at a very small window of time, because I think the 6th problem there was a statistics problem. Is that right?
Yes.
Yeah. So I did take that problem off. I guess I don't know. It seemed like there was enough. There was enough to do with just differential equations. I was going to kind of stick with that. But if you want to talk about that, that's also fine. Statistics is not my thing. I mean, actually, differential equations is not either. So it's a bit of it's easier for me to talk about differential equations though than statistics and say anything useful about it. Whoever you have teaching statistics will not be me.
As much as you can. Just a tiny bit. If there's something I don't know what to do, I just don't.
Okay. All right. Well, good. Okay. So I mean, that was a question about the homework. That wasn't really much of a question. So any other questions about the homework or about last week's homework? I mean, I did post solutions. I haven't had a chance to grade those at all. So we'll see what actually ends up happening. I'll see if I can get around to it or not. Otherwise, I'll just give you the points. But I would like you to look at those and sort of see what was done and compare them with what you did, and see if you have some questions there about any of that stuff. I guess in particular, just looking at these. I guess I'll go ahead and share my screen. Okay, so I think we're sharing this screen. To move all this stuff out of the way. Whoops, did not mean to do that. Whatever I just did. I don't know what I'm doing. Let's see, I think people are still coming in. Nope, okay. Let me just look at this real quick. So this was last week's homework. These are the solutions. So one of you, I looked at your homework somewhat, and so I'm just going to talk quickly about last week's homework and things to maybe watch out for. One of these two things was in the first one of these two things was a vector space, one was not, right? If you're going to show something's not, I'm just going to talk through things that I would look for if and when I get around to grading these. If you're showing something's not a vector space, right? You just need to show one axiom fails, right? So one simple example. So in this one, I think you can see this. So in number 2, this is not a vector space because, well, one of the things vector space have to have is they have to have the 0, right? The 0, and these are actually a question about subspaces, right? So the vector space here is R3. Are these things subspaces, right? To be a subspace, you have to have the 0 of the vector space, and the 0 of this vector space is just 0, 0, 0, right? And that is not in the second one, right? So there's one simple axiom. You can just say, this is not a vector space because, 0, 0, 0 is not in here, right? It's not a subspace. For the first one, to show something is a subspace, you have to verify closure. In this case, you have to verify closure under scalar multiplication and addition, and also that 0 is in there, right? Showing that 0 is in there is just straightforward. You say, well, 0, 0, 0 is in here because 0 plus 0 plus 0 is 0, right? So you're done. But the rest of it, you have to be a little bit more general about, right? You have to take two things which are in S1. And this is the thing that I did see one person's work on this. You can't pick your favorite things, right? You have to take two arbitrary things that are in S1. So just UNV, whatever they are, right? This may be U1, U2, U3. This is V1, V2, V3. The properties that they have is that the sum of those entries will be 0, right? That's what it means to be in this S1 here. And you need to show that the sum is actually in S1, right? And so, I've worked all that out for you here. So just make sure you understand this, right? So when you're doing a proof, you can't do a proof by example, right? When you're doing a proof, you have to do a proof, right? So that's the point. Any questions about that? I mean, does that ring a bell to anyone? Sort of spark any alarms or anything? Just okay. Number 2 was pretty straightforward. I think the intent was maybe for you just to show that this is a vector space by proving all the axioms. That's a little confusing because of the A cosine x, B sine x thing. It actually, to me, is so many of the things you're trying to show seem so trivial that it's hard to figure out what you're supposed to show. So what I did was a little bit different. So a standard example of a vector space is all functions, say from R to R. In fact, all functions from, well, no, that's a good one. So like all functions from R to R is a vector space, right? And so this set you're looking at here in number 2, well, it's a subspace of that vector space, right? I mean, these are, everything in this S is a function from R to R, right? So it was easier to show that that's a subspace. That's kind of clear what you need to show. I need to show if I take two things in here and add them together, I get something in there, and that's pretty clear, right? So that's all clear. And then on the side, what I did here in my solutions, right, is just showed that this space, the space of all functions from R to R, is itself a vector space, right? And to me, that made more sense because it's more clear to see what the axioms are saying in that case, right? So that's the reason I did it this way. But again, when you look at my solutions, if you have questions about why I'm doing things the way I'm doing, that's the kind of thing, like, ask questions if you have them. Okay. Did anyone have a question about that? Do you look at the solutions? Yes
Dr.
or no?
K, it's Jordan. I'm gonna be honest. I didn't get a chance to look at the solutions. I actually, and not to go on a big tangent, but I actually proposed last Thursday. I was in North Carolina, so I was driving down. So I didn't get a chance to do a lot of things. I did like one of the homework problems, and then I started the other, and then my attention got kind of divided. So my questions, I'm holding my questions because they're more about the current homework rather than the last. So.
Okay. Okay. So anyway, I mean, I'm just trying to get, do look at the solutions. And my guess is you probably will have questions about what I'm doing, right? Because maybe I'm doing a little bit more than you would do. Anyway, just make sure you kind of understand them. So yeah, I mean, if there's no questions, we can go on. I did put some code in here if you want to see that code. One of you did a nice thing with this last one. You made your tables in MATLAB. I like the way you did that. I mean, there was one small error in what you did, but I like the way you did that. Here I used Excel to make these tables. You know, the again, there's another proof here. I mean, the thing that's going to cause you the most trouble as you move forward into the other classes is proofs, right? There's a lot of proofs. A lot of the classes are based around proofs, right? So the other one in here that's sort of a proof-based thing was this number 5, right? Which was showing that this Zn is actually a ring, right? So there's these axioms of rings. You need to show it's a ring. How do you actually do that, right? And so you have to sort of, in this case, it's like unpacking a definition. Like, you know, in Zn, the elements are 0 through n minus 1. How do you define addition? Well, you add 2 things in there. Now you may get something bigger than n when you add 2 things, so you have to do mod n, right? And that's the definition of this. And then you need to know something about modular arithmetic and the way it works, right? So if I do a plus b mod n, it's the same as a mod n plus b mod n, all mod n, right? You might want to think about why that extra mod n has to be there at the end. And then, so here's a proof of that down here that I gave you. And then you use it for proving things, like here's the distributive law, right? So in your case, you needed to prove the distributive law, you know, associativity, commutativity, all these things, right, that you're supposed to prove for being a ring. The main tool you need to use is this thing up here that I called a claim, right? You had to use that, something like that somewhere, right? Something like that had to be used. But then you should have basically a, you know, this kind of proof, right? There's a proof right there, and it, you know, it says why each step is correct, right? So like here, I'm just trying, you know, I'm sort of expanding this thing, like what does this mean, right? Well, what does multiplication mod n mean? Well, it means take a as an integer, right, and multiply it by this thing as an integer and do mod n, right? So, you know, that's just by the definition of you know, multiplication mod n, right? Same thing here. What does this c plus n mean? So here I'm just expanding this in terms of the definition of what, you know, plus mod, you know, plus n and times n is. Right, and then I'm using this claim in order to sort of pull these mod n's out of the whole thing. Then, you know, using distributivity in Z, right? So, you know, I'm saying each line, like why the thing I'm looking at is true, right? So, you know, sometimes when you write down a proof of something like this, you ought to do something like that. Make sure you put in all the reasons, right? Very often when you write proofs, they're more like paragraphs or something, right? But this is a case where it's like if you were having students turn in algebra work, right? And they were solving a system or solving an equation, right? And they had to show step by step what they're doing, right? So something like that. Anyway, take a look at it, and if you know, I don't know, if you do have questions, ask. Otherwise, when I get it graded, you might have questions why I graded it certain ways. But to some extent, in all future courses, for the most part, you will look at your own homework and the solutions we give you, and you need to make sure you're doing them correctly, right? The majority of the grade in the class is coming from the exams. So I grade all the exams very carefully, assuming you've taken the homework and done it, because that's where you learn a lot of stuff, right? And you've compared it to you know, to my solutions. Someone asked about a book for this class. This class is just touching on lots of little topics, so there's no book for this class, right? In all the future classes, you'll definitely have text. Okay, so just this class is weird because we just do random things in this class. Okay, so now did someone want to ask me a question about this week's homework? Otherwise, I can talk about, so I did make some notes, and I did put in, there's a video, there's 2 videos now, so I just finished one video, and I'll add the last video at the end. If we don't run into anything else to do, I'll talk about some of these notes. Now, since we've already got the 2 videos in there, I might focus on the last bit more. But if you have some questions about the homework, I'm happy to answer that first, or about the DQs. I mean, any of this stuff we're doing.
Professor K, it's not that I think that I get that was a quick read for you, but the language that's being used in the first half of this class is a more sophisticated way of speaking through the math language and understanding how to write a proof. Writing proofs in high school is not as detailed as what we've been reading or what I've been reading. I can only speak for me. And if this is something that I'm going to need in future classes, I would prefer to do some pre-work and have a book where I can start understanding the way the assignments are going to be expected to turn in, rather than taking a hit on my grades and then going, okay, well, I needed to learn how to do it this way. I'm one of those, let me do it ahead of time
Well,
so that I can be successful, because my grades matter to me. I mean, I get it, it's not that important, but it is kind of thing.
right.
Does that make
So when
sense?
you get a text, the way you learn to do proofs is by reading proofs and doing them. That's how you learn to do proofs, right? There's not like any sort of magic trick there. So when you're in a class that has a text, you definitely need to be reading the proofs that are in the reading that you're doing, and either in the text and also in the notes that we give. And you should be not just reading them, you should be working through them yourself, right? You should be trying to do them yourself, see where you get stuck, get unstuck, right? So try to do the proof yourself. When you get stuck, look at it and get unstuck, right? Then you will have plenty of homework. You will have lots and lots of homework, right? With complete solutions to most of that homework. And like I said, you need to compare what you're doing with the solutions that are given, right? And if you have questions about where there's differences, you should ask, right? I mean, a lot of the learning is on you, right? A lot of the learning of how to do proofs is by doing proofs, right? And by reading proofs. So there's no real way around that. There are books like, let me see, can that even, it doesn't show up because of the filter thing. Let me just turn off the filter for just a second. Oh, okay, let me turn off that filter too. Okay, for just a second, right? I mean, there are books like this, like How to Read and Do Proofs, which you might get hold of, right? So you can just look up for books on how to do proofs, right? So that's a thing you can do. I'm not sure it's, completely useful, but it might be useful, right? For just, it'll step you through certain things. But really the way to do it is to read and do proofs, right? To do the home. I mean, really you learn an awful lot of stuff by doing the homework and not just doing it, but making sure you did it the way we expect to see it done, right? And again, usually, at least in my classes, right, there's not a grade hit for that. Like you do the homework, I give you the solutions. Your job is to do the homework yourself and then compare that homework with the solutions, right? So that you can see. So there's not a hit on the grade there, because basically if you turn them in, you'll get the grade. Where there is a hit is when you get to the exam. If you haven't been doing that, then you won't know what to do in the exams, right? I mean, that's where we really test you, right? The homework is your place to learn, right? And then the exams for other classes. I mean, this class is different just because it's this intro class, right? But that's sort of how things will be there, right?
So, Dr. K, my concern is close to Crystal questions about number 5. So when I try to prove, I just put like the properties like associative, distributed, but I didn't show like details at the way that you show us in the homework, the answers for the homework. So I don't know if that hit the grade, because as this level, I didn't expect like we have to show like how can I use associative or commutative properties. So again, it's all about to learn how can we prove. So
yeah, but so I guess the point is, I mean, so that's the thing, right? So look at my solutions, right? I'm not even sure if will get a chance to grade those. So I want you to look at my solutions and see what I'm doing, right? And then try to work through those again. So one thing you can't do when you're doing a proof is just state the thing you're trying to prove, right? You have to actually prove something. You have to do it, right? And so in that one, that's a good example. So let's take a really easy one. So let's look back at the ZN again, right? So that's the thing, right? So again, you have to make a definite, you have to know like, what is this structure? How is it, how is it defined, right? And there's actually more than one way to define this structure and how to define addition on it, right? So one way is to take this structure to just be 0 through n-1. I mean, this is another problem, right? In this case, we're choosing a representation for this structure, and we're choosing this one. So just the number 0 through n-1. Those are the remainders, right? So those are the things that are remainders when dividing by n, right? So that's clear, right? That's clear. Okay, so like one of the things you need to prove, for example, well, let's take a really easy one. Let's show that 0 is 0, right? I mean, that's a really easy one. That's one of the things you need to prove, is that there's an additive identity, right? So that's a thing you need to prove. So you know, added. So here we have additive identity, right? So what is additive identity? I mean, what does it literally say? It says that for all x in my structure, which is Zn, right? You know, x plus whatever the plus is of the structure. In this case, the plus is this plus sub n, right? Whatever the thing that 0 is should be x, right? And actually, it needs to be kind of two-sided, so it should also have this. Should also be like this, right? So no matter which side I add 0 on, I should get x, right? So I mean, that's the definition, okay? Now, this particular one is commutative, so you actually could do just one-sided, right? So we haven't proved commutative yet, but that's something to do. So this is really, really simple, right? So all I'm doing here is I'm taking something from in here, right? So here, how do we prove this? So when I want to prove a for all statement, right? The way you do this, now this is stuff we kind of talked about in week 1, is you just say, let something be an arbitrary element in Zn, right? So let A be an element of Zn. I haven't picked my, yep.
Not to cut you off. Do you have to state explicitly that X is an element in Zn, or is that just what you're about to prove with A in Zn?
I mean, you mean in this first expression?
Yeah.
Well, so I mean, this is getting a little bit into so the language here is, you know, this kind of first order logic that we talked about in week 1. So the assumption here is that this is being interpreted in some structure, right? And the structure it's being interpreted in is this structure up here, right?
Gotcha.
So when we write this for all x like this, we're really saying we're really talking about that structure, right?
Okay.
So I really don't need to say for all x in Zn because that's just part of what we're saying, right?
Gotcha.
So if we were being super, super, super formal, and no one is this super formal, right? I would say that Zn together with its operations, let me make this a little bit bigger so I've just a tad more room here. You know, and then we had like the 0 of n, right? It thinks, it models, so that's the way we would use that. You know, for all x, that's, you know, stuff, right? Whatever I wrote down there, right? So really in this full statement, it says in this structure, it is true that this sentence holds, and that is the satisfaction. That's like the is true in that structure relation, right? This is way beyond anything we're gonna, I mean, you don't have to do stuff like this, right? But that's kind of the intuition. The intuition is when you write a sentence like this, you're doing it inside some structure. You don't always make that structure completely clear, right? I mean, like when we're doing calculus, sorry, we're sort of taking another sidetrack. You know, we say things like for all epsilon greater than 0, there's a delta greater than 0, etc., right? And the assumption is that we're working in the reals here, right? We're talking about real numbers, not something else, right? So there's always this kind of implicit assumption about where you're working, right? So anyway, hopefully that's kind of clear, but also whenever you have implicit assumptions, it can be confusing, right? So that's part of the problem. But now coming back to this particular one, right? When I'm trying to prove a statement that starts off with for all x, right? The way you typically do that is you take an arbitrary thing. So let A and Zn be arbitrary. Now, really, you don't have to say this because it's kind of assumed, right? Sorry for my handwriting there. But that's a lot different than saying let 2 be in Zn, right? And picking the number 2, right? Or something like that. That you can't do, but I can let A and Zn be arbitrary, right? And then now I want to prove this fact, you know, that fact. So I want to show, I'll just, sometimes you even say this, need to show. I mean, remember, you're not just trying to prove something to see that it's true. You're trying to explain what you're doing to whoever's reading this thing, right? So it doesn't hurt to tell the person who's reading it what it is you're doing, right? I mean, surely you've all graded stuff from students and you wish that the students would tell you what their thought process is, right? Not just write down a bunch of symbols, right? Because that doesn't really help much. You really kind of need to know what you're doing. So we need to show, right, that A plus n 0. Now what is 0? 0 is just the 0 from the structure Zn, right? I mean, it has a 0 in it. So my claim here is that normal 0 is the 0 here, right? Now, what is A plus n0? What is this thing defined as? By definition, now here's where you need to use a definition. This is defined as A plus 0, Now this is just treating a as an integer, right? Mod n. Whoops, mod n. Okay, but a plus 0 is just a, right? So that's just a mod n. Right, and a was taken as something that was a remainder, so it's already less than n, so a mod n is just a, right? And so this is a simple proof that a, you know, when we're doing the plus of this structure with 0, we just get a back, right? So it almost looks like we're not doing anything. Let's do another one that's maybe a little bit more interesting. Let's show that there is additive inverses, right? So now that we have a 0, we need to show, so we need to show that for all x in the structure, right, there exists a y in the structure, right, such that x plus n y equals 0, right? Now this isn't quite so clear, right, because there's not, so given 2 in the structure, and in Zn, right? Let's take a specific example, like 2 in Zn. There's not a -2. It's not there, right? So you can't just say choose -2 because there isn't such a thing there, right? So there is something to actually do here, right? So again, you say let a, so this arbitrary x, let a be an element of Zn. I need to come up with something now, right? This says take something arbitrary. This says produce something with some property, right? There is something with some property. What works as the additive inverse modulo n? So what number do you add to get back to 0, so to speak, mod n? So let's say I'm in Z5.
Is it n?
Well, it's not n. So let's say I'm in Z5, right? And let me take this example of 2 again, right? What is the additive inverse of 2 in Z5? What do I add to 2 in order to get 0?
3.
That would be 3.
Yep, you had 3, right? So 2 plus sub 5 here, right? 3 is 0, right? Because 2 plus 3 mod 5 is 0, right? So that's how it works, right? What is the additive inverse of 1 mod 5?
4.
4, right? So over here, I'm looking at a specific example to get some intuition, right? That's kind of the idea here. That's something you should do when you're trying to work through proofs. Look at examples to get intuitions, but that's not a proof, right? So in each case, 3 is equal to 5 minus 2, right? So the additive inverse of 2 was 5 minus 2, right? The additive inverse of 1 was 5 minus 1, right? So let's come back over here. I have an arbitrary a and Zn. What would the additive inverse?
So n minus a?
N minus a, right? So, so here we can just say consider. Okay, so you see the difference? Like over here, we're sort of looking at example to get an intuition, to make a guess, so to speak. Over here, we're going to prove that that guess works, right? So consider b equal to n minus a, right? Then we have that a plus sub n, b, well, let's just write b here first. B is a plus sub n minus a. By the way, why is n minus a in Zn? Well, a is something in Zn. And in particular, a is between 0 and n minus 1, right? So n minus a is still something in Zn, right?
Right.
Because this will still be a number between 0 and n minus 1, right? And then what does this mean? Well, this means, and here's where we're sort of expanding this definition again. So this is a plus n minus a computed in Z mod n. That's the definition of this plus sub n down here, right? Okay. And this, of course, is n mod n, right? But n mod n is 0, right? So now we do get to use, this fact that equality is transitive, right? So I have a plus n b is equal to 0, where b was this n minus a, right? So I've taken an arbitrary thing in Zn, I've come up with a b, such that a plus nb is 0, right? So that's what we needed to prove this additive inverse thing, right? Right, so you can't just say it, you got to prove it. But there we go, we proved it. We actually had to create something along the way, right? Kind of like if you're doing an epsilon delta proof, you need to come up with a delta for every epsilon such that something happens, right? So you have to create that epsilon, you have to create that delta for every epsilon. Let's do one more. So I did in my notes, in my solutions, I did distributivity. Let's do commutativity too. I mean, this one's even easier than distributivity, but here what I want to show, whoops, let's try that again. Okay, what I want to show is for all x, for all y, x plus ny equals y plus nx, right? So I need to show that, right? So again, so now here I've got for all, right? So you just say let, a and b be arbitrary. In fact, again, you don't really need to say that. It doesn't. You need to think it. You need to sort of know that's what you're doing. Arbitrary elements of Zn. By the way, if you want to look back at the week 1 logic stuff, this was that what was called universal generalization, right? Where I can take an arbitrary a and b, prove something, and then extract from that for all x, for all y, something or other, right? So I take an arbitrary thing, and now I'm going to just try to prove this. So a plus nb, right? We still have to do something. So again, you have to expand what this plus n is. This is a plus b. Now this is just in the integers, mod n, all right? Because remember, a plus b might not actually be in Zn minus 1, right? I mean, I might be in Z5, right? And this may be 4 and 4, so we get 4 plus 4 here, right? So that's no longer in, between 0 and 5, right? Right, but now I do have commutativity in Z, so this is the same as b plus a mod n, right? So to get from this line to that line, I'm using commutativity in Z, right? So I mean, if I wanted to say why these are true, this is, by definition of plus n. Going from here to here, this is by commutativity in Z, right? And now I'm going to undo that definition of plus n. So this is the same as b plus na, right? Because again, this is by the definition of plus n. You remember the first week, a lot of you said that a implication was trivial if it was by definition, right? I mean, that was a common answer to that. What's the difference between vacuous and trivial implications, right? Lots and lots of what you do when you're doing proofs is unpacking and repacking definitions. So, I mean, a lot of what you're doing, according to that definition, would be trivial implications, right? But I would tend to disagree. I think unpacking and repacking definitions is not really all that trivial. That's really where a lot of the work is some of the time. Okay, so I mean, that's commutativity. Do you kind of get the idea? You have to do something here, right? You can't just say it's true, right?
Yeah, I think this was way more clear than how it was last week. So
okay, good.
Speaking for myself.
Okay, good.
I agree.
Good.
Thank you.
Yeah, sure. Good. Okay, now do you want to ask me some specific questions about the homework you're working on? And then I will sort of just start talking about differential equations and stuff. Today's work is mainly computational, right? There's not really proofs today. It's mainly computational stuff. So any questions about the homework? Like, are any of you struggling with a particular problem in the homework right now? Otherwise, I'm going to just go through some of the stuff in the notes.
So I did complete all 5 of my problems, but once I ran across something that showed that let me go.
Whoop, you just muted yourself. Sorry.
Did I unmute myself? Okay. So on my notes, let me turn back to my page on my notes because I've just been doing a lot of research and a lot of practice problems. And I ran across, after I did the delta theta divided by delta r divided by delta theta, and solved that problem, problem number 3 from the homework. Once I got to the end, I found that there was conversion formulas because delta, those are polar coordinates. And so my wondering was, were we supposed to turn those back to linear coordinates so that we would be able to take the differential equation of them before, or did we just leave them as polar coordinates and apply differential equations? Because this is a first order linear differential equation, but these are polar coordinates. So that's what my question was in the classroom was.
So the answer to your question is there's no real interpretation of anything there as being polar, right? There's just these two variables, which you're wanting to call polar because they're r and theta, right? But in any case, the relationship you're given is between r and theta, right? Not between some other x's and y's, right? So you're not really sort of getting into all that. The
so
actual
then I don't need any
problem
help.
was.
I understood it.
Can you just remind me what it was though? It was like r.
It's delta r. I mean, it's dr divided by d theta equals theta r squared d theta. And so we just have to isolate the variables on one side.
Wait, no, it's not that. It's theta. It's just theta r squared, right? Is that what it is?
Theta r squared, yeah. So we have to
Like
multiply both sides by d theta and then take the integrals of both sides.
Yeah, that's exactly right, right? So if this, if this had been like, dang it, this had been like dA over dB, right, is equal to AB squared, it's exactly the same, right?
Right.
I mean, in this situation, it's saying, I've got these two variables, I'm telling you about a relationship between them given by this differential equation, right?
Mm-hmm.
You don't need any extra outside information beyond that for this particular problem, right? And so this then is and what was the method called here?
Separate the variables.
Yep. So this is separation of variables, exactly right. So so this would, you just convert it to this, and then you would integrate both sides, right? This one up here, you do exactly the same thing, right? It becomes dr over r squared, right, is equal to theta d theta.
I only asked because I ran across one that said that was supposed to change to dr divided by dt and then d theta divided by dt. And
no, there's
I'm just saying the example that I ran across. I totally did it this way initially, but I just kept trying to find practice problems to memorize the processes and memorize the steps. And then when I ran across that, that's why my question came up. That's the only reason.
So the example you're finding is doing more, right? It's doing something where we're actually looking at polar coordinates, right? So it's doing something else. That's kind of not actually here, right? I mean, you could do lots more with this. Like we could do this, like make this dr. I mean, you know, when you're actually doing calculus, you might make this dr dt over d theta dt.
Yeah, right? That's what I ran
do all
into.
Sorts of stuff, right?
Yeah,
so that's just not what's going on right here in this problem, right? So like, yeah, I mean, that's a good question, right? So that's a thing that you're learning too, is when you're going out and finding sources, to be able to pull out what's relevant, non-relevant in the particular examples you're finding, right? So that's part of what happens here. By the way, in the proof thing, you know, it wouldn't be a bad idea if you're struggling with proofs to use. AI is not bad with proofs, right? It wouldn't hurt to, if you're struggling with those, to run your proofs by chat or something like that and use it as a kind of tutor, right? To see how it, you know, see what it thinks about your proofs, right? Won't always agree with what I think about your proofs, but it is sort of a first step in kind of practicing, right?
And which one do you use, Professor?
I use both Gemini and Chat, and they're both good in some places where the other one's bad. So it's kind of a mix. And now,
have you tried Pilot yet? I've not used any of these, so I just know that those are the 3 top. Because Microsoft is
Copilot is, I think, related to Chat. I'm not exactly sure, but I think it's somehow related to GPT. I think they have an agreement, so I think they're not completely different.
Okay.
But I mean, it's a new tool you have that we didn't used to have, right? So it is a tool that I think might be useful for this kind of thing. Trying to make it into a tutor, but just like where you looked up something and got this extra information, it's real easy to get led down a false path that way, right? Because it doesn't really know what you're trying to do, right? So you do have to be careful, but it's, for initially doing proofs, it's not a bad tool to try to use.
Thank you, sir.
Yeah. Any other questions about the homework?
I had a question.
Yeah, go ahead.
I had a question on number 4, where there was a double zero, and in the notes you had lambda does not equal lambda, but in this case it does because
Here, let me
it's a
see.
double
So
zero.
I don't actually have it open. Homework. Where do I have the homework?
It's y double prime plus 4y prime plus 4y equals 0.
Okay, yeah, if you can just tell me. So it's then you get to see me try to work it on my own. So y double prime plus
4y prime
4y prime
plus 4y equals 0.
plus 4y equals 0. And okay, and so there's actually
That
two
just means
methods.
it's homogeneous, right?
So this is homogeneous and it's linear. Why is it linear?
Because there's no squared terms in it. There's no other exponents raised higher, I believe. It's all linear.
So yeah, so that's a good. All right. I mean, this is a good thing to think about here, right? And so what is it a linear combination of? Like what is the
Y.
So it's so the things that are being combined linearly are these 3 bits of stuff, right? So these are being combined with these coefficients, right, which are in this case just scalars, right? So this is a linear combination of these things here, right? So that's the reason this is called linear, right? So there's no terms of the form y squared or y prime times y, or things like that, right? These are just combinations of those things there. This is a linear. So what's another kind of linear thing might be something like this. I mean, I could have sine t y double prime minus cosine t y prime plus 3y equals 0. Right, so this is still considered linear. Now the coefficients are now these functions, right? This is still a linear differential equation where y is the thing we're trying to solve, right? So the difference is these are linear differential equations, linear second order differential equations with constant coefficients, right? And this would be a linear second order differential equation with non-constant coefficients. Okay, but there's no y's in there. And in this case, they're both homogeneous because of the 0 there at the end, right? So that's the different sort of pieces of this thing. If you get rid of the 0 and you allow non-constant coefficients, things start getting much harder. So in this class, we're just barely touching on it. We'll stick to these kind up here, right? So that's kind of so now let's get to the actual question that was here. So let me get rid of all this stuff. Okay, so this is the one we're given. Okay, and now let me just indicate in my notes this may be confusing to you. So there's another way, and I'm going to say this is a good way of thinking, but it might take you a while to believe me, right? That this is a good way of thinking. Maybe you will never believe me, but I'm going to say it's a good way of thinking. I'm going to write dy as another way of just sort of writing y prime, right? So that's like an operator, right? So d, right, is now a function going from, I mean, what's it actually operating on? It's operating on something we might call d1 of r. So the set of differential functions on the reals, and what is it going to output? Well, it's going to output the derivative. So that's some other function on the reals. Doesn't even have to be continuous necessarily, right? So it's just some function on the reals, right? So this is a vector space, that's a vector space. This is a linear operator, right? So we know that if I take the derivative of y plus z, right, I get the derivative of y plus the derivative of z, right? And if I take the derivative of 5y, I have 5 times the derivative of y, right? So this is a linear operator on these two spaces here, right? There's a lot of kind of linear algebra hiding around in the background here. So this thing up here I could write as I apply the differentiation twice, right? And here, was there a minus sign in this problem, or was it just y double prime? Was it minus y double prime?
No, no minus.
Just y double prime. So it'd be like that, plus 4d, because it's just a y prime, plus 4, and now this is like d squared, this is like d to the 1, d to the 0, right, which is really just the identity. It just doesn't do anything, right? So you might write d to the 0 as the identity, right? So that y is just y, right? So that's a way of doing this. So we get this thing. So instead of writing this, I'm just going to leave the 4 there, okay? So I'm just going to leave it like that. And then we have y, right? So when I apply these operators to y, I end up with this thing up here, right? And now we're interested in when this is 0, right? So not the number 0, but the function 0, right? The 0 function is what we're interested in here, right? And now on this side, we have a quadratic, right? And so if we can split it up, if we can factor it, right, then we get this equals 0, right? And well, it turns out, now this is, you have to think about this some, that if this product of this gives me a 0 function here, then one of these things have to actually be the 0 operator, right? So if this is giving me 0 here, it must actually be the case that d minus lambda 1 of y is 0, or d, or maybe both, d minus lambda 2 of y is 0, right? But this thing here just says dy equals lambda 1y. This, whoops, lambda 1y, right? So this is a linear operator applied to something is equal to lambda 1 times that thing. This should immediately make you say eigenvalue, eigenvector, right? That's the sort of things we're looking at here. And this over here is d y equals lambda 2y. So another eigenvector pair where the eigenvectors are differentiable functions, right? And then the lambdas here are just scalars, in this case, maybe from the complex numbers, right, is often the case here. Because we're solving, you know, a quadratic, right? So we get complex numbers all the time. And you know how to solve these, right? So writing this another way is just y prime equals lambda 1y, right? And over here we have y prime equals lambda 2y, right? That's what we're getting from these two things, right? So we know the solution to this thing is you know, so a solution here is y1 equals e to the lambda 1t, whoops, lambda 1t, and then times some initial value, which I'll just call y1 of naught, right? Or maybe just k, I'll just call it k, k1, right? And over here, you're getting the same sort of thing, right? y2 equals e to the lambda 2t, then k2, some constant, right, on that side, okay? So I mean, thinking, so you've got two ways of doing this. You can say, oh, I'm going to take this thing, right, that I was given, and just remember to turn it into a characteristic polynomial, you know, whatever letters you want to use, plus 4, right? And factor that and get these two lambdas and then use some magic that tells me the answer is going to be stuff like that, right? Or you can think of it as actually doing something. I'm actually factoring an operator, right? And I'm just using the fact that the only way this operator can give me 0 is if one of these pieces is 0. And so I'm reducing it down to these pieces, right? And then I'm solving that because I already know how to solve those things, right? I know, you know what the eigenvalues are. I mean, this is a good question. What are the eigenvalues for the differential operator on differentiable functions? What functions have the property that lambda, that dy is equal to lambda y? So this, again, this says the same thing as y prime equals lambda y. So what are the solutions to things like that?
So are you okay for both way if we did the characteristic equation?
Yeah, but I would like you to know what's going on. I mean, you won't have me teaching you differential equations. So, you know, whoever's teaching you might do whatever they do. I don't know. But I would like you to actually know what's going on, not just memorize stuff, right? You're not here just to memorize how to do things and learn magic tricks, right? Hopefully you're here to learn math, right? And so that would be my hope. But anyway, all that said, right? What is the only thing? What are the functions that satisfy this guy here? Y prime equals lambda y. What are they? You know what they are. Or we could even do what we did a minute ago and use separation of variables, right? I mean, because we could write this as dy dt equals lambda y, right? So we could then write this as dy over y equals lambda dt, right? And so we can integrate both sides, right? So on this side, I just get lambda t plus c, right? On this side, what do I get? So I have dy over y. Do a u substitution if you like. What do you get here?
Natural log.
So it's the natural log of absolute value of y, right? Like that. So we can raise both sides. You know, we can do e to both sides, right? And so you get y equals e to the lambda t plus c up here. Of course, here we can break this up into, you know, this is the same as e to the lambda t, e to the c, right? Now, I guess here we have an absolute value, right? Literally, we have an absolute value there, right? So in this case, this, you know, c was an arbitrary constant. So this is an arbitrary positive constant, right? So we can just call it c again. And we can get rid of the absolute value and just let it take any value, right? So we have e to the lambda t times c, right? So the solutions are this one-dimensional subspace, right? We're multiplying by any scalar, right? This is the vector. Those are the vectors. That's the eigenvector, right? It's a one-dimensional subspace in the space of differentiable functions, right? So an infinite dimensional vector space. And these are the eigenvectors right there, right? And we know that they satisfy dy equals lambda y, right? That's what they satisfy, right? So those are the things, right? So there's a lot of good, solid math here. There's no magic trick here, right? We're just sort of literally figuring out what these solutions are, right? Now let's go back to our problem, because I've totally lost the problem. It was this problem way up here, right? So let's let me just rewrite
Professor,
it.
can you save your notes, please? Please don't delete them. Can you save them?
Yeah,
So
but
you
then
can
I also
share
give
them
you
with us.
the videos, so you can always go back and watch them too. I mean, sometimes my computer glitches and I can't actually save them. So I will say I will try to save them, but I can't. So this was our original thing. Let me just chop it out so I have it here. Or let me make a copy of it so I can bring it down here. And can I just paste it? Or how do I do that? Oh, actually, I don't know how to paste it. Ah, phooey. I don't know how to do that. I have to drag it or something. Oh. No, I don't know what I did. Let me undo that. There. Okay, that's it. So y double prime, 4y prime, 4y. Okay, let me come back here. So y double prime plus 4y plus 4. Okay, and I think I'm finally getting to the question that you asked a long time ago. So the way I'm doing it, I would call this d squared plus 4d.
I think, sorry, sir. I
4.
think it's y prime prime plus 4y prime.
4y prime, right? Plus 4, yeah, 4y. Sorry, there you go. Right, and so in terms of the operator, it's this thing. So this is 4d plus 2 y, right, equals 0, right? Yeah. So so I could even add more notes to my. So this is a square here, right? So this is a tricky one because we're getting an order 2 root, right? So our root here is actually -2, right? We're getting d of y equals -2y. Oops, y, right, is what we're getting for one of these, right? So we get one solution, which is what? From this, what do we get? Y equals what? So this is just y prime equals
C1.
So some
time.
C1,
Yeah.
okay.
E to the power of -2x.
-2, okay, x. We'll we'll take x instead of t, but yeah, okay, so
Okay.
there, right? Now this is a tricky one because okay, now, and again, here we have to get back into the theory some. There's a lot of really nice theory here, right? So these are homogeneous solutions to an operation, right? So you have this operation, d squared plus 4d plus, essentially the identity, right? Operating on, on the set of differential equations, differentiable functions, right? And they're giving us 0. So these are called the kernel of this thing, d squared plus 4d plus I, right? So it's the set of all things that map to 0, right? So that's like before we had the null space of A. We've already seen this a couple of times. So it's the same kind of thing. It's like the null space of the kernel. Those things that map to 0. The theory actually tells us that the dimension of this has to be 2. It's 2-dimensional because of we're not proving this in this class for sure, right? But because of that 2 there, this is a 2-dimensional subspace. This kernel has to be 2-dimensional. And right now we just have one thing here, right? So what will we take to be our other solution? We need another solution, right? So now this is, again, I'm not going to call it a trick because there's a nice way of using the same sort of thing to do this, but I don't want to delve into all that right now. But someone tell me, what is another solution here? This is where you might have had to research it yourself a little bit. So I need
C2 C2 x e to the power of negative 2x.
Yep, that's right. Right. So it's like that. C2x to e to the minus 2x, right? And so if I were to run this same operation on that, let's sort of see how this works. So I have d plus 2 squared. That's my operator, right? And now I'm applying x e to the minus 2x on this, right? So when I do it once, I have d plus 2. Maybe I'll put the I in there just to make that clear. And then I'm going to run it once, d plus 2i on this thing, x e to the minus 2x, right? And what are we going to get when we do that is we're going to use the product rule, right? So I get here e to the minus 2x, right? Plus, let's see. Sorry, I have to be a little bit careful here. So yeah, this is, I'm doing the d. Yeah, okay. So the d is going across there and doing that, right? So getting
Professor K, is the d the determinant?
No, it's the differential operator. So dy is equal to y prime. I just want to make it look like an operator instead of like a prime, right?
So if we use the determinant method to solve this, do you expect us to come back and do it this way and turn it in your way? I'm going to do it your way anyway. I'm just curious.
There is a determinant. So I do talk about that later in the notes, systems of equations. So you can do this that way, right? And so this is another way of doing that. So either way is fine, right? If that's what you mean, like where you take the second order differential equation and turn it into a system of first order differential equations and then use the determinant, right? So I definitely have that in the notes, and that's a thing that we can talk about. But here, if I just so this is just the derivative, this is just 2i, right? So I take the derivative of this, right? And so the x just goes away, right? And I get e to the minus 2x. And then when I take the derivative of this other part, right, then the x stays, and I get a minus 2. Whoops. So I get a minus 2x e to the minus 2x, right? And then the 2i just sort of duplicates this whole thing. So I get a 2x to the e to the minus 2x here as well, right? Because that's what happens when I take this 2i and apply it to this thing, right? So I just get it back again, multiplied by 2. The 2 is there, right? Now what happens here is that cancels, right? Those two things cancel. So after I applied this operator once, I'm left with just this thing, and the rest is like this, right? Okay, but we chose this thing. This thing is exactly going to give us 0. That was the whole point, right? That's how we got to this e to the minus 2x in the first place. This is the part that gives us the eigenvalue thing, right? So we can run it, right? If I do it again, right, then I take the derivative here, I get minus 2 e to the minus 2x. That's from taking the derivative, and then 2 times this, which is plus 2 e to the minus 2x. Right. So sort of the reason putting this x here works is because this is really running this operator here twice, right? And using the fact that you have the product rule to sort of make things work here, right? So this, you think of it this way, kind of explains why putting the x there works, right? The other option you have, again, I'm just sort of giving you options, is when you get to a situation like this where you have a repeated root. So where was this originally? Right, we have a repeated root here. Like if we just do the, you know, the characteristic polynomial, right? We get, and let's use a variable, I don't know, r, right? R squared plus 4r plus 4, right? So this is r plus 2 squared, right? So this is the way you usually teach it in a first pass at a differential equations. You just take the characteristic polynomial, you factor it, you get this. We have a repeated root, right? So you know that one of the solutions is going to be e to the minus 2t, and the other one is this magic thing. You just put an extra t here, right? By some sort of magic, this works, okay? And then you combine these some way, right? So anyway, I like this way because this sort of running this operator once on this thing kind of explains why it works, right? So I like explaining why things work instead of just saying, here's some magic that works, right? Now, once we've done that, right? So we have two solutions now. We have e to the minus 2 x, sorry, we were choosing x, right? And we have x e to the minus 2x, right? And then we have unknown coefficients, right? So our kind of, so this is now a two-dimensional space, right? So the vectors here is that's a vector and that's a vector, and it's a two-dimensional space spanned by those two vectors. And these are the set of all solutions to that differential equation, right? And then we know it's a set of all solutions because we know that solution space is a two-dimensional subspace, right? So that's coming from the theory, right? So that's not at all clear, right, that that's true, but that is true. It's a two-dimensional subspace. So that's a thing to prove when you take a real differential equations class, right? Is that that's what you have. If I had a third degree polynomial, it would be a three-dimensional. If I had a third degree linear differential system, you know, homogeneous differential system, it would be a three-dimensional subspace, right, etc. Right. Okay. Even in the case where the coefficients are not constant numbers, even when the coefficients are themselves functions of x, it's still a three-dimensional solution space, right? So that's a thing that you would prove in some class at some point, right? The thing is, if they're
question.
Yeah.
In three-dimensional, so we add that we have that operator moving, and that's where we get the x from. So does it give us an x squared, or does it do something different?
We would have to, I mean, we'd have to start by coming up with a, like if I had d plus 3i cubed as my thing, right? So what is x plus 3 cubed? Can someone tell me? It's x cubed plus 3 squared times what? 6? 6x, is that right? Plus 3 times the 6x squared, right? Plus 3 times 6. Wait, what am I doing here? 3 squared. No. 3 times 6x squared, and then 3 squared times 6x plus 3, right? So our differential equation may be y triple prime plus 18y double prime
27.
plus 9 times
27.
6.
27, yeah, at the end.
Where?
It says 3 squared 6x, the last term is plus 27.
Oh, 3 cubed. Sorry, 3 cubed down there. Right. Right. And then 9 times 6 is 54. Y prime plus 27 equals 0, right? So there's a system, right? So the claim is that is really d plus 3i cubed, right? And then again, we're getting just one solution. So the one solution we're getting here is e to the minus 3t, right? That's the one we're getting from just sort of looking at that directly, right? And now we would like to answer the question, is it the case that if I take this and do what to it, right, to get what comes next? So let's see, does t e to the minus 3t still work? right? It would give me a 0, right? Will this still give me 0, right, when I'm done? Right? And the answer will be yes, because that argument will be exactly as before, because when I just apply this twice, that'll happen, right? So let's try it with t squared. So let's do that, right? So let's do t squared e to the minus 3t, and then let's apply this thing. So I will have 2 of them out here, and then I will apply it once here, right? And so when I apply it once here, so what's going to happen here is I'm going to get a 2t e to the minus 3t. That's coming from taking the derivative of that and leaving that alone, plus t squared, plus, and then a minus 3, right? So let me get that in there. So I'll get a minus 3 t squared e to the minus 3t. That's from taking the derivative of that, right? And then this sorry, this should be a 3i here. And this 3i here will be plus, so it would be 3 times this thing, right? So it'll be 3t squared e to the minus 3t, right? And see, that works again, right? Those 2 terms cancel each other out. That's why it works, right? And now I've got this part left over to apply to that, right? But we've already checked that that one's going to go to 0, right? So that'll 0 out, right? Yep. So the next one up would be t squared e to the minus 3t. So it's a nice technique if you understand what it's saying, right, and what it's doing, right? Sort of showing you
Absolutely.
why it works, right? It's not just some sort of magic trick, which I don't like magic tricks in math. I mean, I don't know. Sometimes I do, but not usually. I like visual magic tricks, like. Oh wait, no, you don't want me to erase this, so let me keep this. Okay. I think we've more than completely answered that question, right? There was another pseudo question, and that was, can we do this with sort of systems and eigenvalues and stuff like that, right? So I would kind of like to look at that too, maybe. So let's see, in the notes, I have some stuff about integrating factors. I don't know if anyone's tried one of the integrating factor questions. Like suppose your thing was more like y prime plus 2y equals 3, right? So that's not quite in the right form now, right? So now we have to do something else with this thing, right? To do this. I mean, let's just try to do it. I have no idea what will happen if I try to do this, right? I have an example here in the notes, but let's just see what happens here. So how do we actually deal with this integrating factor? So this has the general form like this, y equals q of t. So that's kind of the general form. So again, we have these functions, these functions that involve the variable t, they're like constants here, right? They're sort of like constants in this case. And the trick here is to take this new function that we define, e to the integral p of t dt. So it's e raised to the integral. Let me try to write that better. Like that, right? Now let's think about what u prime is. So u prime, right? I'll take the derivative of p of t dt. By the fundamental theorem of calculus, the derivative of an integral is just itself again. So that's just p of t, right? And then we get e to this thing, right? But that's just mu again, right? So the derivative of this mu here is p of t times mu, right? So that's what we get. Okay, so over here, if I multiply both sides by mu, I get y prime. I'm going to say this kind of falls into the realm of tricks, right? Not quite a magic trick, but sort of a magic trick here. And then over here, I get p of t y mu. I'm just multiplying through by mu, q of t mu, right? So I just multiplied both sides by mu. That's all I did here, right? But on this side, so this part here can be rewritten as mu prime y, because mu prime was that, right? And so this turns out to be y prime mu prime y. Well, that is just mu y prime. Again, that's using the product rule, right? And so this is equal to qt mu, right? So that's nice because now we can just integrate both sides, and this side just sort of goes away, right? Because mu y, right? And then we have this integral over here, right? So now we solve for y. Y is equal to mu to the minus 1, not the inverse, but just 1 over mu, right? Integral of qt mu, dt, right? And these are both functions of t, just to make this clear, right? This is mu of t on dt, right? So you get, and this is, mu inverse t. It's not an inverse. This is one, maybe I should not write it like that. Let's just write it like this. 1 over mu of t, just to make that clear, right? Okay. Now this presumes quite a few things, right? So it kind of presumes that I can, take this integral up here, and it presumes that I can take this integral here, right? So it's sort of assuming a bunch of stuff, right? That things will work out. So let's actually try this with this one. Now I just made this one up on the fly, so I have no idea what will happen with this, right? So y prime plus 2y equals 3. So with that one there, right, let's try this. So this is the P of t, right? So the integration factor is e to the integral 2 dt, right? So that's e to the 2t, right? And then the point is that I get y mu prime is equal to mu times 3, so 3 e to the 2t, right? So I get that. And I integrate both sides, so I get y mu is this e to the 2t equals integral 3 e to the 2t, right? And what's the integral of 3 e to the 2t? It's like 3 over 2 e to the 2t plus some c, right?
Plus c, yes.
Okay, and then now I want to isolate y, so I'm going to multiply by the inverse. That's the 1 over mu part, right? So y equals 3 over 2. E to the minus 2t times e to the 2t is just 1, so that goes away, right? Plus c e to the minus 2t, right? So I get that, right? So this one worked out nice. So I get this solution, right? Now, in order to get a specific solution, I would need to specify an initial value, right, there as well, right? So I didn't do that, right? So it's not quite complete, right? But it's only a first degree differential equation, right? So I only expect one parameter here in this thing, right? Okay. Good. Let's see. In the examples here, the examples I gave you for this. Let's see, separable. Oh, no. This is different. Wait, I'm confused about what I did. Sorry, hold on just a second. Let me think about what I'm doing here. Oh, right. Okay, right. So what I did, yeah, so in the example, I tried to make the example somewhat meaningful, right? So now, of course, adding all this information actually makes them harder, actually, but it makes them sort of more real world, right? So this one here, where we're looking at the equation is just y prime equals this, right? And this was just the very simple y prime equals ky is all this is. Well, no, it's a little bit different, right? So this is a cup of coffee cooling, and the law is, and that's what's written here, right? The law is that the change in temperature of the thing that's cooling is proportional to the current temperature, the difference between the current temperature and the ambient temperature of the space, the room, right? So that's this differential equation, right? Where this T naught is fixed, like you have a room and it's being kept at a specific temperature, right? And this is just a simple separation of variables, and you solve it and you get an equation like this, right? So I'll let you look at that if you want. If we want to work through it, we can. This is the one kind of like what we just did. This is a integrating factor one, right? And the example here now that leads naturally to that.
I do want to work through it, Professor, if you don't mind, because first of all, I didn't know where you got the formula from. Are we supposed to know that from ourselves? Is that something that's going to be given in the equation? when I was going through your notes, I got lost quite often because I was like, okay, is this something I'm supposed to already know from this word problem? Or is this something that's going to be given to me in the word problem? And if so, where did it come from?
Well, I mean, this isn't a class on physics, right? So I mean, I'm just coming up with examples of differential equations. That's what I'm focusing on here, right? So this was an example of a separable differential equation. So I'm just sort of explaining how to solve the separable differential equation. That's his method here, which you applied earlier, so you know how to do that. And then I want an example, a real world example of such a thing, right, where it comes in and is used. I can't make a real world example of something that has all of, every real world example has lots of extra details that there's no particular reason everyone would know all the time, right? So I mean, this particular one used this law of cooling, right? But this is all part of the setup, right? I mean, this whole thing is the setup. The only thing you're asked to do is solve this differential equation, right? So the setup is that you have this hot cup of coffee at 90 degrees Celsius. It's placed in a room where the temperature is kept at 20 degrees Celsius. And after 10 minutes, the coffee cools to 70 degrees Celsius, right? So there's some initial values hidden in this thing. How warm is the coffee after 20 minutes, right? So that's the question. This is part of the setup still. I mean, it's telling you this, right? But if you were in a physics class, for example, you would probably learn this. So we have Newton's law of cooling, right? And the law of cooling states that the rate of change of temperature is directly proportional to the difference between the temperature of the liquid. So this is a liquid, the cup of coffee, and the ambient room temperature, right? So that's a sentence in English stating a law of physics, right? And then how does that interpret into math? Well, it interprets into this differential equation, right? This is the differential equation it turns into, right? The rate of change of temperature of the liquid, that's this d. I mean, there's two t's, right? So d capital T, d little t, is directly proportional. The minus sign's there just so that the K turns out to be positive because the temperature is decreasing, obviously, here. And then this is the difference between the current temperature of the coffee and the ambient room temperature, right? So that's what this is. So this is like one of those questions you ask algebra students in some sense, except for the dt here. You give them some sort of direct proportionality statement in English and say, turn this into a mathematical statement, right? So that's what this part is. And then we have this thing which we need to figure out how to solve. Well, that's this section, right? This section is on solving separable differential equations. So now we've got this differential equation we want to solve, and we just follow that method, right? So I separate the variables, dt over t minus 20 on this side, minus k dt on that side. You integrate both sides, right? So you get natural log, absolute value of t minus 20 is equal to minus kt plus c, right? This is just this c there is coming in from the integration constant, right? When we integrate that side, so we get that c. We take the e to both sides, right? And so on this side, I would get t minus 20 equals e to this stuff over here. I mean, maybe do I need to write that stuff down? So I mean, here I've got ln t minus 20 equals minus kt plus c. That we got from separating the variables and integrating, right? Now I'm taking e to both sides, right? And so this becomes e to the minus kt, e to the c, right? But again, this is just an arbitrary positive constant, right? So I can just call this c e to the minus kt, right? And then on this side, what do I get? Well, I'm getting t minus 20, absolute value, right, is equal to c e to the minus kt. Now we're only interested in cooling, right? So this number is going to always be positive in this problem. So now this is part of the context, right? So we get that t minus 20 is equal to c e to the minus kt. And so t, as a function of t, right, is equal to c e to the minus kt plus 20, right? And now what do we have here? We've got, so that's the solution. We just have this c and we have this k. Right, we need to figure out what those things are, right? And so we need two pieces of information, and we have two pieces of information, right? So it starts off at 90 degrees, so t of 0 is 90 degrees, all right? And so when I put in a 0 there, that becomes 1, so this is c plus 20, right? So c is 70, so that we get, right? And then the other thing we have is that after 10 minutes, it's 70 degrees, right? So that's the other thing we have. By the way, what kind of problem is this? This kind of came up in one of your DQs this week, right? I'm not giving you two initial values, right? I'm giving you values at two different times. So this is a what?
Boundary value problem.
It's a boundary value problem, yeah.
Yeah.
So this is T of 10 is equal to 70, right? And so now we put that in there. So I've got, so C is 70. So I have 70 e to the minus k times 10 plus 20, right, is equal to 70, right? And so from there, then now you're just sort of solving some stuff. So 70 e to the minus kt, k times 10 equals 50, e to the minus k times 10 equals 5/7, right? So taking natural logs, so minus k10 equals natural log of 5/7, right? And so k is minus 1/10 natural log of 5/7, right? Whatever that is, it's a number, right? And so we can put that in. In fact, we don't even need to evaluate it because we can just work this out. So this is 70 e to the minus k, so that's going to be just 1/10 ln 5/7. That's minus k to the t, right? T plus 20, right? And of course, e to the ln 5/7 is just 5/7. So this is 70 5/7 t/10 plus 20, right? So there's a nice closed form for this cooling thing, right? So that's a nice closed form for that. So my next question was, so I did have help. This is where I did use AI to do this, right? I said, give me a nice problem of this kind, right? So the next one I say, give me a nice problem of this kind, right? And see if you can relate it to the previous one. And well, it came up with a nice case where I'm taking something and putting it into a greenhouse where the temperature in the greenhouse is not constant. It's not a constant ambient temperature, but the temperature is actually a function now, right? So the ambient temperature is given by this thing over here. So, you know, in a 24-hour period, it vacillates this way, right? So it's a sine. You know, so it starts out at some temperature and goes up and goes down, right? But it does that every 24 hours, right? So now the temperature of the ambient room is changing, right? So now you're taking something at a certain temperature and putting it into an ambient room, but that ambient room temperature is not fixed, it's changing, right? So where does that change? So, I mean, this section is all about this kind of problem. So why do we get that kind of problem here? Well, that's in all the sort of setup stuff, right? So the ambient temperature is that. So the Newton's law of cooling is the same. It's still the change in temperature is proportional to the current temperature minus the ambient temperature. But now this ambient temperature is not fixed. It's a function, right? So that's where the difference is. And when you work that out, when you sort of plug, so the ambient temperature is that, and you plug it in and you get this thing here, right? So now we've got down to this point where we have this thing. So all of this is the setup, right? I mean, this is all being given to you. And then we get this thing here, 0.2 t equals 4 plus sine pi t/12. All right, so we get that. So this has exactly the form. Remember, the form that we're looking at here is y prime plus p of t y equals q of t, right? So this is the part you need to recognize. That's y prime, that's t prime, right? This 0.2 is the p of t, right? So that's that. And this function on this side, well, that's the q of t, right? So that's that part there, right? So the initial step is really easy, and then it starts getting hard to find stuff, right? So the multiplication, the integration factor was mu, which was e to the integral p of t dt, right? So in this case, that's e to the integral of 0.2 dt, right? So that's just e to the 0.2 t, right? So that's our integrating factor right there, right? Integral to the 0.2 t, right? That's the integrating factor. And so what we get here is we get that t mu prime, right, is equal to this integrating factor times that. So e to the 0.2 t times 4 plus sine pi t over 12. Okay, right, so we get that. So now we're going to integrate. So we integrate this, both sides. Well, so let me not write it here. So we integrate both sides, right? So on this side, I get t, and remember this u is just e to the 0.2 t, so e to the 0.2 t. And on this side, now I get this thing, which we're going to have to try to, well, I mean, we're not going to do this now. We're just going to look at what the answer is. All right, and so we get t, so this is what we're after, t of t, right, is equal, so now I divide both sides by that, so it's e to the minus 0.2 t times this integral here, right? So the integral e to the 0.2 t, whoops, come on, e to the 0.2 t times all this stuff, right? So 4 plus sine pi t over 12 dt. Okay. So, I mean, in some sense, we're finished, right? So what I said in the notes is to some sense, when as soon as I get down to where I'm just doing an integral, right, then I can sort of claim that we're done, right? So here, this integral has to be done. So in the notes, I actually do it, right? I do all this stuff. But this is the main thing, right? We got our t of t, we've got it like this. Okay, it's given in terms of integral. In order to do this integral, you have to do some, what do we call it? Integration by parts, right? You got to do a bunch of stuff along the way, right, to do the integral. And then also along the way, you end up getting some C, right? You get this c here that sort of pops out at the end because we're doing some integration, right? We'll get some c there, and you have to use the initial values to figure out what that c is, right? So I'm not going to work through all this because this is a lot of just computational stuff, right? So you can look at this and work through it, right? The point was that this is one of these where you need an integrating factor, so it's different from this kind up here where you didn't need an integrating factor, right? So that was the main thing. And the second thing was that the example is very closely related to the previous example, right? So the first example was cooling with a static ambient temperature, and this is cooling with a functional ambient temperature, right? And so the difference in method are these two differences in method, right? Okay. I mean, I could have done this without giving any examples, but I thought it would be nice to put what we call real world examples into things, right? Because people love having real world examples. But let's be honest, real world examples are complicated. They complicate things, right? They make things harder a lot of the time. And that's the case here, right? But it's good to know that these aren't just random things mathematicians do. These are things that can be used to compute stuff that people are interested in, right? That's a good thing, right? Anyway, a lot of stuff on that. Same kind of things in the notes here. So we're already at 6:30. Simple oscillating motion. So first of all, is there any question? Again, I'm skipping a lot of this detail because this is just Calc 2 type stuff that you have to, I don't know, remember, look up in a table, ask MATLAB to do. I don't really care, right? It's just you're doing an integral, right? By the way, just to keep this in mind, lots of integrals you can't do, right? You can't do this integral, right? You can't do this integral. Whoops, this integral. I mean, these certainly exist. Like I could say, you know, integral 0 to t of that thing, integral 0 to t of that thing, right? There's no form that you can't write down the integral of these things in terms of simpler functions or other functions that you already know, right? These are kind of brand new functions, if you like, right? I mean, this function here is called erf(x), whatever that is. It's an error function, right? And this is whatever it is. I don't know what it is. I think it does have a name, but I don't know what it is. Right, but these are completely new things, right? So there's just new functions. It's not unlike other things. I mean, like what is this? I mean, to an algebra student, you know what x squared plus 1 is. That's an easy thing, and we do you know, integral dx over x squared. So this is the integral of a rational function, right? Surely it must stay a rational function. It can't get too crazy, can it? But what is this actually? Who knows? Yeah, I see you mouthing it there. This is arctan, right? right? So if you take a rational function and you integrate it, you can definitely end up with transcendental functions, right? So generally when you integrate things, the class of functions become more and more complicated, right? So the same thing here. I mean, it's easy to write down things you want to integrate that you don't know what they integrate to. So I mean, part of this, a lot of this sometimes becomes doing things numerically, right? But in this case, we can integrate it if you know enough integration. So you notice I'm trying to keep these in some sort of order, right? So there's some first order differential equations with fairly simple methods, a couple of second order differential equations. First one really easy. So the first one's sort of like, where did the first order one started? It started with this one, right? So the second order one, starting with this one, which is very close, right? Very similar, right? but still a little bit different. So this one here, you know, I mean, you just like here, we recognize the answer is EKT, right? You just sort of see that, right? You look at this and you know the answer is sine square root of KT, right? Because if I differentiate it once, I get cosine, I get square root of K cosine, right? Differentiate it again, I get another square root of K, so I end up with a K out here, right? And then I keep the minus sign, so I have the minus sign, right? And then I'm back to sine, right? So if I differentiate this twice, I get exactly right. So if I do this twice, I'm at minus K sine square root of KT, right? And in some sense, there's no difference between sine and cosine. Cosine square root of KT is also such a thing, right? Okay. Sine square root of KT and cosine of square root of KT are linearly independent functions. I can't get from one of these to the other by taking a linear combination, right? So these are two linearly independent functions that are solutions to this thing. This is a second order differential equation. So I know, again, from the theory that we're not really getting into, the dimension of the solution space is 2. I need 2 solutions, and then from those I can derive any other solution. So I know that any solution to this guy up here is going to be a linear combination of those two. Sine square root of KT. Right, so my sort of general solution here would be that, right? Again, how do I know I have all of them? Well, that's from some theory that says if I have 2 linearly independent ones, this is a 2-dimensional space of solutions. That's all of them, right? So that's kind of the idea there. Okay. Good. Okay, so that's that. And then the first example I have here is a spring system. And this is the typical first example. I mean, this is where people in physics first run into these things, right? Is solving spring systems like this, right? So this is, you know, Hooke's law, and it's a spring, and you solve it using this thing, right? And so again, whether or not you know Hooke's law isn't the point here. The point is that Hooke's law gives you this differential equation. That's the point, right? And so once we know that, we know how to solve it. And there's a few more words that come up here, like we have a mass. It's displaced by 5 centimeters from equilibrium. So I mean, the picture's like this. I've got a spring like this. It's got some sort of spring constant. You know,
I got a question, Professor. I get that they're going to give us that equation, but when I'm reading the text, how do I know that that's a differential equation? I guess that's what my question is that I appreciate you giving me an equation, but how do I know that when I'm supposed to integrate versus when I'm supposed to take the derivative? And when I'm supposed to use matrices and vectors to solve, because these are all, I see you using these examples, but I don't know when I'm supposed to use which.
Well, I think you're expecting maybe a little too much, right? This is not a course in differential equations. This is 1 week where I'm exposing you to a lot of little bits of differential equations, right? So there's a lot of stuff being thrown at you, right? I mean, here you're recognizing it's a differential equation because Hooke's law here is stated as a differential equation, the way this is, right? So I mean, that's kind of the reason you're recognizing that it's a differential equation here.
Can you tell me the vocabulary that tells me it's a differential equation? That's where, because it says y double prime, that's why I know it's a differential equation.
Yeah, I mean, this is the
Okay,
form
got
of
it.
differential equations we're looking at right now, is exactly this form. Y double prime is minus ky. That's what we're looking at, right? So this thing satisfies Hooke's law. I mean, what's really going on here is it's like mass. So it's force is equal to mass times acceleration, right? And so this would be like the zero displacement. So this would be positive and negative displacement as this thing vibrates back and forth like that, right? So this would be like y. This amount of displacement would be y. So the velocity that it's moving would be y prime. The acceleration would be y double prime. So this is my double prime, right? Is what's going on there, right? And then Hooke's law says that the force is proportional to the position of the spring, how much it's stretched out or compressed, right? Either one of those things. So that's where this is coming from, right? So that's where we get this. So that's the physics kind of behind this. But once we have this, well, this is an equation of the form I'm interested in. That's the point here, right? And then the rest of this is just sort of plugging in this solution, right? We're kind of getting late on time, so I won't do this. I mean, it's here. You plug in this general form, and then you have to solve for the coefficients, right? The only other thing here is you're told in the problem that it oscillates 2 times per second, right? And so that's one thing that's worth remembering is that frequency. So the 2 times per second is what we call 2 hertz, right? The hertz isn't important, but the point is frequency, the number of oscillations per time unit, is 1 over the period. So that's a thing to remember, right? And so in this case, we have the 2, which is the frequency, is 1 over the period. Now here we have some basic, I don't know if you call it just like pre-calc or something, right? So we have sine square root of kt. We don't know k yet, or do we know k? Oh, no, we do know k. K is in this problem. Oh, no, we don't know k yet. I guess we don't know k yet. Is that right? Oh, I'm finding k. What am I thinking? I'm finding k. So what is the period of that? So the period of sine t is 2 pi, right? So what's the period of sine ct? It'll be 2 pi over c, right? I mean, that's just the way scaling works, right? So the period here is 1 over 2 pi over square root of k, right? So that's square root of k over 2 pi, right? And so from this, we get that square root of k is equal to 4 pi, right? And so k is equal to 16 pi squared, right? So we actually get our k there like that, right? So that's where that's used. So the frequency is being used to get the k in this case, right? Anyway, the final solution here just turns out to be 5 cosine 4 pi, so that turns out to be easy. And you're just plugging in. This is an initial value problem, right? I'm telling you, y of 0 is 5 centimeters. Y prime, it started out at rest. That's part of the problem. So I start off with 0 velocity, right? So that's that thing. So here we're given y0 and y prime of 0. That's the initial value. And we're using that then to find this specific solution, right? So that was this form, y double prime equals minus ky. Obviously, a more general form would be this. So y double prime plus a y prime plus cy is equal to 0, right? So this one here is again a linear second order constant coefficients, constant because these things are just constants, constant coefficient. Right, so like that. So previously, I guess we did I'm not sure what I did. I feel like I did something like, somehow we were talking about this before. I guess we've already talked about this to some extent, right? And so this is just exactly what I'm doing here. I'm saying this is the method I was talking about before. Yeah, I guess we've already kind of done this, right? So in this case, again, I wanted to make this example look like the previous example. So I did a damped mass spring, right? So now we've got a spring, we've got a mass, it's sitting on a table, but now there's friction, right? So you pull it, you let it go, and it goes back and forth. But if you sort of plot it with respect to time, maybe it does something like this, but it slowly stops and comes to rest, right? That's the point, right? So it's a damp system, so it oscillates slower, right? Sort of does something like that, right? Okay. You could have the opposite. You could have a system that blows up instead of damping, right? So that can happen too. And that happens in nature. I mean, if you've ever seen like this video of a bridge hitting just the wrong frequency in the wind, right? And the whole bridge just starts shaking and falling apart, right? That's from exactly this kind of, the opposite of damped oscillations, where it kind of explodes like that. Anyway, there's a problem here, which is, again, it's a Hooke's law problem. There's a damping force. All the physics is sort of explained here. The point is that's the equation we get, right? We end up with that equation right there. This is definitely one of this form, 2y double prime plus 8y prime plus 20y equals 0. You can divide out by the 2, right? So you end up getting one exactly of this form, y double prime plus 4y plus 10, right? And so, oops. Come on. Oosh. Plus 10 equals 0, right? So the whole little spring system there turns into solving that differential equation. One way or the other, you look at the characteristic function, or you look at again, the way I was writing it was like this, plus 10, right? Like that, you factor that, or you look at the characteristic equation. Either way, right? You get the roots, and the roots are going to be, the two roots are going to be -2 plus or minus I square root of 6, right? So this happens a lot of the time. You get complex roots like this. This part is going to turn into the damping part. That's going to cause the damping. This is going to be a trig part, right? So just to remind you of one thing that maybe some of you have forgotten. E to the IT is cosine t plus I sine t, right? I mean, there's a very close connection between complex numbers and trig functions, right? So that's definitely used a lot in this in the rest of this, right? Okay, and then the rest is kind of just painful computation, right? We've got some initial values. We've got this beautiful number out here that's kind of a pain to work with, right? So y of t is equal to this, right? It's just c1 e to the, let's call it lambda. Let me do it like this, right? So let's say lambda is one of these, -2 plus I square root of 6t. Sorry, it's that, right? Oops. Lambda bar, which is the conjugate, would be -2 minus I square root of 6, right? And so our solution has the form c1 e to the lambda t plus c2 e to the lambda bar t, right? For those two things right there. Okay. Anyway, that's what this solution is, right? And because the lambda has this -2 bit, so just to look at this, so either the -2 plus I root 6 t, right, is e to the -2 t, and then the rest of that is e to the I square root of 6 t, right? So again, this is the damping part, right? As t goes to infinity, that part goes to 0, right? This is the trig part, right? This is cosine. This is cos square root of 6t plus I sine square root of 6t, right? So that's the trig part. Okay. Okay. So then y prime. I'm just taking y prime here, right? And then we've got these two initial conditions. We have c1 plus c2 is equal to 0.1. This is all in meters. And I think we had moved in the problem, it was 10 centimeters. So this is 0.1 meters. That's where this is coming from. And the initial velocity again was at rest, right? So y prime of 0 was 0. And so you have this linear system, c1 plus c2 is equal to 0.1. And then this, right, which is a linear system in the complex numbers, right? So you can solve it. Anyway, this is all just stuff, right? So I'll let you look at that. You can work through it yourself, or it's good to try to work through yourself. It's good to try to remember how to manipulate complex numbers. It's not a bad thing at all to try to remember how to do, right? If you're afraid of complex numbers, graduate math is probably not the right place, right? Complex numbers are really, really important things to know, right? Anyway, I'll just leave that. So again, the point here, there's a lot of writing here, but the point is this is the form, right? That's the main point of this section, right? And then there's an example which sort of matches up with the previous example, a damped mass spring system, right? So that's that. In the last few minutes, so I was asked about when use one method, when use another method. There is a second method for these things, right? So the second method is to change a second order system into a first order system. Change a second order linear equation to a first order system of equations, right? So, and then when you do that, you bring in matrix methods, right? Now there's a lot of linear algebra here, right? I mean, when you get to matrix methods, you run into linear algebra right off the bat, right? So just like we started with this very simple equation, y prime equals ky, right? We get as a solution y prime equals e to the kt, right? And then times y of 0 actually, right? The initial value at 0. Right, so there's this very simple way of solving this thing, right? When you're given a system which now has a vector of derivatives, right, and it is equal to now not a constant number, but a constant matrix times a vector of functions you're trying to solve for, then the solution is, oops, I wrote this totally wrong. This is not y prime, this is y, right? Y equals that. Then the solution y is this vector version of e to the at, and then the initial value, for the values of the y is at 0, right? So this initial value problem, right, like that. So very likely this is something you've never seen before, right? What is e raised to a matrix? Right, is probably something new. And so I'll just briefly say what it is, because I can just give you some I'm not proving any properties or anything. I'm just giving you some definitions at the moment. But e to the, so first of all, e to the x, what is e to the x? One way of defining e to the x is summation I equals 0 to infinity, x to the n over n factorial, right? You can't just define e to the x that way, and you can prove all of its properties, like the derivative of this thing is itself, all these sort of properties you can just prove directly from this. Okay, this is the definition. E to the a is summation I equals 0 to infinity, 1 over n factorial, so that's the usual n factorial, then the matrix A to the n. Right, so we can do that. That's a thing we can do. Generally, this is, of course, not terribly useful because raising matrices to high powers is hard, right? But in a very special case where I can take A and I can write it as some matrix times a diagonal matrix times some other matrix, well, times the same matrix inverted like that, okay? So this is called conjugating D by this invertible matrix S. Again, something you'll see a whole bunch when doing algebra, conjugation type stuff. What happens here then, this e to the a, right, is really the same as summation I equals 0 to infinity, it's 1 over n factorial, and then this is s d s inverse to the n. Okay, but here's why conjugation is so nice, because s d s inverse to the n is really s d s in, whoops, dang it. S inverse in many of these. Right, but these all can't, I've got S inverse S, those all cancel out. They all cancel out along the way. So this just becomes SD to the N S inverse. Right, so I don't need all those S's around. And the nice thing is, what is so let's say that this is D1 through Dn, right? And I raise it to the kth power. So raising a normal matrix to the kth power is a lot of work. Raising a diagonal matrix to the k power is not. It's just d1 to the k through dn to the k. You just raise the power of the diagonal elements, right? So it becomes really easy to do, okay? So sort of writing this thing out. So this e to the a, right, becomes s, and then summation I equals 0 to n, to infinity, 1 over n factorial d to the I. But sorry, I've got n's and i's. I got too many n's and i's. Let's call this I factorial d to the I, right? But what is this d to the I? So, and then s inverse at the end, right? So that the s just factors out of both sides. So this becomes summation. I'm going to write it out in a little sequence of things so you can see exactly what's going on. I didn't type all this stuff up because it's a pain. So 1 over I factorial, and then this thing here would be like d1 through dn to the I, right? And then s inverse at the end, right? Okay, but I can bring the summation inside this thing, right? So I get s, and then over here I get summation I equals 0 to infinity, 1 over I factorial, d1 to the I, and then all the way down to summation I equals 0 to infinity, 1 over I factorial, dn to the I, right? So I get this diagonal matrix, an S inverse. And well, what are each of those things? Well, that's just e to the di, right? So this is just s, e to the di, e d1 through e to the dn, S inverse, right? So it's really quite amazing. So this e to the a, which I define with this infinite series of matrices, as long as it's diagonalizable, right, is really just s, and then you just diagonalize you just raise the diagonal elements of the diagonal matrix to the e. Okay, and this is a general thing that happens when I can diagonalize matrices and I'm applying a function to them. Very, very often I can just say, well, what the result is this S and S inverse, this kind of change of basis matrix, and then that function applied to the elements of the diagonal matrix. Right, so it becomes really nice. This is part of the reason you spend so much time learning about diagonalization in linear algebra. Okay. Where does that come in? How do you diagonalize things, right? So so when I have S d1 through dn, and then S inverse on this side, let's think about what this means. So this is some vectors here, v1 through vn.
Before you go any farther, Professor, so when you're saying diagonalizing when you say diagonalizing the matrix, you taught us are you talking about when we get to where we work backwards with Gaussian? Or are you talking about the identity? Or are you talking about where we have the pivots?
Well, wait, so I'm explaining that right now. So let me finish this. I know it's a long little explanation, but let me try to finish here. Okay. So this is d1 through dn, right? And then I have S inverse on this side, right? Oh, sorry, and S inverse is just, so this is S. There's just some vectors, right? Like that. And then S inverse is whatever S inverse is, right? Now I want to apply this to, let's see, how do I want to do this? Yeah, oh, right. So this is A, right? This is just the matrix A, right? I'm diagonalizing A, right? That's the whole point here. So so here I've got, dang it, I keep hitting my pen in a funny way. So here I've got V1 through Vn. Okay, this is S, D1 through Dn. And then on this side, I have SA, like that, right? Well, so what was, sorry, A, I'm multiplying both sides by S, so AS, like that, right? The order needs to be like that. Good, okay, so now remember this S, right, it's just these vectors here, right? I'm trying to show you what these vectors are and what these Ds are. That's the point of this, right? So this is really A, and this is now, again, V1 through Vn. On this side, this is V1 through Vn on this side, and then D1 through Dn on this side, right? Now, when we do matrix multiplication, this is the same, and I actually talked about this some when we did this. This is AV1 through AVN. So I'm just applying A to these various vectors as columns, and that's what gives me the resulting matrix, right? On this side, where I've got these D1s here, this turns into D1 V1 through DN Vn. Right, and so when you look at this, if I'm just going to line up these, columns here, what I get is that AVI is equal to DIVI. So what does that look like? A times a vector is equal to a scalar times that very same vector. Tringle, you keep talking, but I just see your lips moving again. But this is
Eigenvalue.
The same thing we had at the beginning with the AV equals the lambda V.
yeah, this is the eigenvalue eigenvector thing, right? So that's what we get when we diagonalize, when we have A equals S D S inverse, right? And we're diagonalizing. What this diagonal matrix is it's the matrix of eigenvalues. That's what that diagonal matrix is. And what this matrix S is over here is a basis of eigenvectors. That's what that is, right? So diagonalization corresponds to finding a basis of eigenvectors and the corresponding eigenvalues. So that's why all the eigenvector eigenvalue stuff comes up in solving these equations, because that's what we're doing, right? So let me just do, okay, so in this case, I gave you kind of a pseudo example and an actual example. So let's look at the pseudo example, and then I think we're gonna have to stop. So here I've got X, right? I've got, this is a matrix A, right? So I've got X prime as a vector equals AX, right? As a thing there, right? So that's what this is over here. So writing this out would be X1 prime, X2 prime, X3 prime equals, right? And then I've got this array of numbers, right? A11, A12, A13, A21, A22, A23, A31, A32, A33 times X1, X2, X3, right? And I'm thinking of these as being functions of t. That's what I'm trying to solve for, right? So this has this form right there, right? And what I've just said is, well, the solution, we don't even have to think about the solution. The solution is e to the at times the initial value, so x bar of 0. So whatever, x1 of 0, x2 of 0, x3 of 0, that's what that is. That's the solution. We're done, right? Because we're not quite done because this isn't really quite helpful yet, right? So now what we want to do is we want to take A, right? And I want to write it as I want to find a basis of eigenvectors. So it's a 3 by 3. So there'll be three vectors in R3. I want to find 3 eigenvalues. Right? And so this will be the S, and then the inverse of this matrix will be the S inverse. That's what goes over there, right? And so once I've done that, right, then what I have here is I have X bar is equal to S, and then the diagonal matrix, so e to the lambda 1 t, e to the lambda 2 t, e to the lambda 3 t, and then over here I have S inverse times this x bar 0. So I can sort of block that off as a separate thing too, right? So if you compute this, you get some initial vector. I'll just call it u, right? So it'll have u naught, or let's say u1, u2, u3, whatever it is, right? I mean, you calculate this in MATLAB or something. You just do that, right? You compute these things. And then over here, I've got, so on this side, I do want to think of this as the vectors v1, v2, v3. Right, and so what I'm getting here is I'm getting that x1, x2, x3, the vector of functions, right, is u1 e to the lambda 1 t times this vector v1, whatever that vector was, plus u2 e to the lambda 2 t plus this vector v2, plus u3 e to the lambda 3 t plus this vector v3. Right, so you get this solution, right, of like that. Okay. So I mean, all the work is kind of in the diagonalization, and really that's where the work is, right? So this is kind of a pseudo example because it's not a real example yet, right? Remember I said the more details you give, the harder the example gets, right? So this is like a pseudo example. Here's what you need to do, right? And here's what the answer will be. Right, so there's that same expression right there. Okay, so here's a real example, right? And this is the same example from above. It's the same differential equation we just did using the previous method, right? The trick here is to take a second order linear system and turn it into a system of first order things, right? So I can just say let y1 be y prime and let y2 be y, right? And so if I do that, I get y1 prime is equal to, so that'd be like y prime prime is equal to minus 4y1, so minus 4y prime minus y2, right? And y2 prime, which is y prime, is just y1 because that's y1 prime, right? So this thing here, which is a system of first order equations, expresses the same thing this did up here, right? With once I make these kind of changes of variables here, right? Does that make sense? Kind of. I mean, maybe stare at it for a bit offline and think about it. So now I'm getting this y1 y prime equals this matrix times y1 y2. So this is my system, my differential equation as a system. This is my initial value, right? y1 of 0. This is the y1 prime of 0, which we assumed was 0, right? And then y of 0 is 0.1, so that's that. And so we get that system right there. And then what we need to do is diagonalize, right? So that's where the work is, right? So then we take the determinant of a minus ti, we find the roots, that's where we get the eigenvalues from. The eigenvalues are, of course, the same things we found before, right? Minus 2 plus or minus I square root of 6, these very same things as before, right? Then we have to find the eigenvectors, right? So I go through this finding all the eigenvectors here for you, right? So maybe worth looking at, maybe worth just trying to do, right? And then A, here's the diagonal version of A, right? So there's eigenvector for this eigenvalue, eigenvector for this eigenvalue. And then this is just the inverse matrix there, right? So this is the S, D, S inverse, right? Then the inverse is that, you have to compute the inverse. And then I could remember I said I defined this U S inverse of Y naught. So there it is. And so there's the initial value for those U's, right? So that's the U there. And then here's the actual, thing written out, right? So it's a lot of work, right? So the main work is in doing the diagonalization. And then if the numbers become sort of messy to work with, this is a lot of working with, complex numbers and stuff. But this is the same solution we got before, right? So I would say maybe push through this some, look at it, see that it's the same solution, see how the method works. If you want to, maybe just try doing this method in MATLAB, right? So MATLAB has a function called eig, right? So I could enter A equals, so my original A here was what? This, right? So, minus 4, minus 10, 1, 0, right? And I can write, I think the way you write it is SD is equal to eig A, right? And it'll give you the diagonal matrix, it'll give you the eigenvectors, it gives you the S, it gives you the D, right? And you could use that. I mean, you might not get these kind of pretty, I square root of 6 type things, right? But you'll get some sort of matrix here that works, right? And then you can write down your solutions this way. So, I mean, you can do a lot of this stuff kind of in MATLAB, right? You can't even make it do things with square roots. You can do it all symbolic. Anyway, that's sort of a whole different talk, right? But you can do that. So part of the point was that you can do that same problem we did above in a different way, right? And it's kind of useful to see where the same kind of things start showing up. Like these lambdas are the same as that showed up before. The coefficients we get down here are the same. I mean, these showed up in the previous calculation some other way, right? So you can kind of follow that through. Which way you choose to do this is completely up to you, right? So you could do it this way using systems. You could do it that other way, not using systems, right? So you've got both those options. The messy part's still the same. I mean, it's still the same messy part, more or less. And then the last example I give you down here is a non-first order, non-linear system. You can't hope to solve these in any sort of nice analytic way. This is a nice predator-prey model. Here it is sort of just written out for you. There's a vector field. So at each point, I'm computing x prime and y prime and using that as a little vector, showing me how things flow, right? And so a solution would be something that flows through here, so to speak. Think of this as like moving water or something. And then here's some solutions plotted out. Again, all this is done in MATLAB. So I give you the MATLAB code you can play with here too. Not asking you to understand this at all, just as a view ahead of non-linear first order systems, right? So something to think about for the future. Actually, maybe I shouldn't call this first order because there's an XY term. I should just call this a non-linear system instead of a non-linear first order system. So it's something that you will get to, I think, in 550, right? So most of this differential equation stuff you'll be doing like in 550, a little bit in 571, but mostly in like 550, where you're doing the modeling classes. So there's a lot of stuff, right? I think even without talking about the statistics, that was plenty of stuff. Okay, so I've made videos for two parts of this. I haven't made videos for the matrix part. So all that stuff I just said, I will make a video and add for the matrix part, if you want to watch that. Good. All right. And for now, right? Usually we just tell you it. I mean, so Crystal's concern is how do you know what to do each time? Usually at this point we just tell you what to do, right? So in the future, right, when you're in 550, you might have to figure out yourself what to do, right? But for now, that's not really the goal. The goal of this was just to sort of recall to your mind a lot of differential equations, calculus, complex numbers, right? And then just to introduce some of the things you will see in the future, right? And a bunch of linear algebra, right? There's a bunch of linear algebra today too, actually, right? So it's a good point to see why linear algebra is so important. It just comes up everywhere, right? It's like just a basic tool for everything you do. Good. Any questions? It's 7:04. Are we all as tired as I am?
Yeah, pretty.
It's
tight.
9:04 where I'm at.
Yeah, it's
Same.
9:04 where you're at. Okay.
Yeah,
All right,
10
well-
o'clock here.
Oh gosh, sorry. Okay. Thank you for staying awake. Good night. See you next week. Next week will be it. So, all right. See you guys.
All right, later, Dr. K.